Hi, welcome to the Signal Path. In this episode, we're going to take a look at some bleeding-edge RF instrumentation again. In particular, we'll be taking a look at the Rohde Schwarz FE170SR, which is a 110 to 170 GHz RF front-end module. Now, this is much more than just a down-convert mixer. The way Rohde Schwarz has engineered this, it's made it capable of working both with their spectrum analyzers and their oscilloscopes because of the way they handle the LO architecture inside. It has electronic attenuators, and it's completely abstracted away from the end user. So when you plug this in, the measurement plane is at the front of this instrument. Significantly more confidence and reliable measurements can now be made between 110 to 170 gigahertz thanks to this. There's also a transmit version of this that I don't have right now, but there's a lot to talk about. But I want to also emphasize what makes this special and how it compares with other methods of doing these measurements in the past, and we're going to do experiments. So there is a lot to do. Let's get going. Now, in order to appreciate why the Rohde Schwarz FE170 is such a leap forward in front-end modules for measuring these kind of frequencies, we need to take a step back and see how these measurements were done historically in the past. In fact, we could measure near-terahertz signals decades ago by using a very simple diode down-conversion. This is a Tektronix 90 to 140 GHz down-converter module, which I actually showed on the channel, and we reverse-engineered and analyzed it. The EM wave enters the waveguide port, passes over a diode, which is biased externally. And then the LO signal comes in at a much lower frequency, mixes with the RF coming in at a 24th harmonic or so, and an IF signal is produced, which can then be picked up by something like a spectrum analyzer. Now, at the same time, we can have a diplexer to separate the LO and the IF from each other, and that's how it interfaces to a typical instrument. Notice a few things here. First of all, the LO signal has to come from the spectrum analyzer, and it's swept within the frequency capabilities of the spectrum analyzer itself, and therefore this is forced to operate at a very high multiplication factor internally in order to accomplish down conversion. As a result, using a single diode, you need biasing from the outside. This thing has a very bad conversion loss, and as a result, very high noise figure. Its linearity is not very good, and it's going to have poor SNR in general. But nonetheless, you can actually see that a signal is present, and for many years, this is how we were able to look at signals at these very high frequencies. Now, having said that, there is no measurement plane in here that's pre-calibrated. Essentially, the conversion loss table of this has to be manually entered into the instrument and taken into account so you can get a rough idea of what the actual absolute power measurement is at the port here. If you just want to see if a signal is there, it's not difficult. But if you want to do calibrated measurement, you're going to have to take care of a lot of things. And every time you add something to a system like this, it's going to increase the uncertainty of the measurement, not to mention the losses and everything else. And if you want to do broadband measurements, like over a wide IF frequency, the design of this becomes even more complicated, and the frequency response of the IF needs to be taken into account, as well as the diplexer. So as a result, these things were quite limited in the past. And passive frequency conversion continued to get better with the introduction of balanced diodes and balanced mixers, allowing you to get a much better flat frequency response and somewhat improved conversion loss. And we have two examples of that here. These things are still used even today. This is a 75 to 110 gigahertz one from Rohde Schwarz, and here's an HB1 harmonic mixer, also 75 to 110 gigahertz. They had separate LO and IF ports at this point, and you could use an external diplexer if you needed a single port, where a lot of spectrum analyzers began to combine the LO and the IF port of these kind of devices. Now, even though these things had slightly better conversion loss and a better frequency response, they still had a lot of loss because they're relying still on the LO signal coming from the spectrum analyzer, and as a result, you're going to have this harmonic problem that you would always have with these subharmonic mixers. And they essentially give you the waveguide port just as before, and you are responsible for configuring the spectrum analyzer, telling it what's connected, entering the conversion loss tables and everything in order to hopefully make a measurement that has a calibration plane at the input of the waveguide port. Now, the broadband IF response of these continue to be a problem anyway, especially as our needs with these really high frequencies continue to grow. We wanted to do modulated signals at these frequencies. So now you have a problem of how do you do that with an IF signal that is quite a bit limited. So we had to live with these for quite a long time before something better came along. And when Agilent introduced their family of smart mixers, it was a big deal because it removed a lot of the uncertainty and ambiguity of making these measurements by creating an abstraction between the instrument and the user. And this was done by a simple idea. Let's take everything we have, put it in a box, and create a USB port on here. When you connect this directly to your spectrum analyzer, it will download all the calibration and correction coefficients directly from the unit into the spectrum analyzer for it to be automatically taken into account. And the spectrum analyzer would know exactly what is connected, So it would self-configure itself to the right frequency range, it would set the right LO frequency and monitor the right IF frequency, and then everything will be taken care of, and your measurement plane would move at the edge of the waveguide, which was fantastic because it removed a lot of the confusion. But this still suffers from some of the original limitations. This is still a harmonic mixer because it relies on the LO signal coming from the spectrum analyzer at a much lower frequency. So that needs to be taken into account. So these things have about 25 or 30 dB of conversion loss nonetheless. There is no front-end amplification or attenuation or pre-selection, so the instrument has to do software signal ID to figure out what is real and what is the image, but all of that can be mostly automated at the cost of some measurement speed. The IF frequency bandwidth can also be increased, so you can do some modulation frequencies, not very high nonetheless, but it can be because the IF signal coming out of here goes through a different path, but typically on a spectrum analyzer. So this was a huge deal because it made everything so much simpler. And continuing with this trend, Keysight introduced the V3050, which is a frequency extender from 50 to 110 GHz, addressing a lot of the problems and shortcomings of the previous generation smart mixers. This thing has front-end attenuation or amplification, it has banded front-end pre-selection, all electronically controllable, and is fully abstracted away from the user's point of view. Now, this still relies on the LO signal coming from the UXA, and it is tied to that instrument as a result. Therefore, you cannot operate it, at least right now, with anything else. Now, unfortunately, until Rohde Schwarz introduced the FE170, measuring above 110 GHz came again with a lot of limitations. Now, VDI plays a very strong role in this space, and they can make remote heads that measure up to a terahertz without issues, and they do have some critical advantages. Their LO distribution network inside of their modules has built-in multipliers, and therefore their mixers operate at fundamental frequencies, allowing them to have much improved noise figure. But nonetheless, you're still dealing with a box that you have to bring the LO from the outside and get the IF back and connecting it back to the instrument, and these are quite common in the industry. And I think what Rohde Schwarz was thinking, how can we take measurements above 110 GHz and introduce all the additional benefits abstraction brings, make everything as simple as possible for the user, and make it as sophisticated so that it's not tied to a particular instrument at all. You can connect it to a spectrum analyzer, you can connect it to an oscilloscope. How do we do that? And that's the magic of the FE170 we should talk about. And finally, here's the FE170SR, the front-end receiver module between 110 to 170 GHz. Now in the front, we have a WR6.5 interface, naturally, because we do have a waveguide banded input, and we do have the external module connection here, which can connect to smart accessories that directly connects into this. Now this is pretty clever because you can connect, for example, an external amplifier or an LNA or even a filter, and the specification and the characteristics of it will get automatically downloaded into this instrument and then transferred to whatever this is connected to. So as soon as you connect it and you plug it in, you don't have to worry about calibrating all of that. The instrument would automatically move the calibration plane forward depending on what's connected there. This is really convenient and removes a lot of uncertainty from various measurements. And on the side of the unit, we have a small e-paper display which retains the Ethernet settings that the instrument has even when the unit is powered off. This is really convenient because you know exactly what the IP address was without it ever having to be plugged into anything. It's a clever little addition. And the back of the instrument begins to reveal the unique architecture of the FE170 series. So we have the Ethernet port, of course, which interfaces to whatever you connect to. Power, we have USB and the soft power button here on the side. But then we have a couple of SMA connectors here. We have the IF output, which can support up to 10 GHz of instantaneous bandwidth, fully calibrated and fully characterized internally, whatever it is that you're connecting it to. Really handy for making broadband modulated measurements. We also have a reference input and an LO input and an LO output. And this is where this thing really shines. Internally, there's a PLL, and it can provide a fairly flexible reference to the PLL from 10 megahertz up to a couple of gigahertz or so, and that allows you to lock the internal PLL to whatever instrument you're connecting it to. And then you can use the LO input and the LO output to cascade multiple of these. Imagine making a MIMO measurement between 110 to 170 gigahertz with a master PLL in the remote head. And these things have never been done before at this scale, so it's really nice that they're included. Now, I would love to take this thing apart so we can dive in and see what's going on, but due to some IP protection as well as the fact that this is a loaner unit, we can't do that. But I do want to talk about the block diagram of what's inside and how it connects to all the different accessories. And here's the block diagram of the Rohde Schwarz FE170SR, which is heavily simplified, but it should be enough for us to analyze what's going on. I also have the block diagram of the ST, which is a transmit version of this, but we have to leave this for a different video because I don't have the hardware here to show you, but this would be an interesting experiment in itself. So let's take a look and see what we're dealing with. So from the outside, we have a set of smart accessories, for example, that can be connected to the FE170SR, and these are bandpass filters. And as soon as you connect them to the instrument, there's a built-in EEPROM in these modules that once you connect it to the external module, will download the calibration and the response of this phase and magnitude and embed them into the overall calibration of the FE170. So from the user's point of view, you don't have to worry about de-embedding this. It will do that automatically for you. And this is important because the entire FE170SR front end is sensitive from 110 to 170 gigahertz. So if you want to make sure you get rid of all the images, or if you have an imposing blocker signal that you want to get rid of, you can use these filters. This also means as soon as you connect the filter, the instrument will not allow you to measure anything outside of this frequency range, and that can also help not to make errors and so on. And this is a pretty important addition. This is basically a manual, externally selectable pre-selector filters that you can apply to the instrument. Now, after you do that, we have the front-end waveguide input, and then we have a programmable attenuator electronically, which is very helpful, especially if you have a signal that has a large dynamic range and you want to measure across different output powers. You can adjust the attenuation to get the best linearity and noise performance from the 170 SR. And there's an LNA that follows that. So the combination of the LNA and the programmable attenuator gives you the linearity as well as the noise figure of the entire front end. And then what appears to be an isolator, which then feeds into the mixer. Now, as far as I can tell, this mixer should be a fundamental mixer, and that produces an IF signal between 5 to 15 gigahertz or so, and then it has its own amplification and programmable attenuation, and then that goes into any instrument you want. It can go into the oscilloscope, it can go into the FSW, for example, for internal analysis like a spectrum analyzer, and that gives you total freedom. Now, if you look at the LO signal, that's where a lot of the magic of the 170 SR comes in, because it has a complete independent built-in PLL that can synthesize its own clock frequency with very little requirements from the outside. And if you look at this internal PLL, we have of course a VCO or a bank of VCOs internally, and the reference coming in can be either 10 megahertz, 640 megahertz, or it can be 1 gigahertz. And these are the references that come out of, for example, the Rohde Schwarz RTP oscilloscope or the FSW spectrum analyzer. In this way, you can lock this instrument to those units. And then that generates some IF frequencies, and that IF frequency can be between 8 to 16 gigahertz. And if you want to cascade multiple devices, or if you want to provide your own higher frequency LO in, you can do that via these ports. So if I use, for example, the LO out of one 170 SR into another one, then they are coherently locked, and then that way you can make all kind of measurements that are synchronized, which is quite nice. After that, we have a doubler, another doubler, and then going out of this module into another doubler yet, and then an amplifier into the mixer. Now, I think there should be another doubler somewhere in here, which is probably not shown unless this mixer is operating on a second harmonic, because I don't think a times 8 frequency is sufficient to combine all the way to 170 gigahertz. So perhaps there's something missing here. Maybe Rohde Schwarz can clarify that for us. But this means that now you have a fully independent internal PLL, and you don't have to worry about anything coming from the outside, and this thing has good enough phase noise to compete with the kind of LO signals that you were getting from, for example, something like an FSW. So a very powerful combination. And let's take a very quick look at a couple of the important specifications of the FE170. So you can see the frequency responses from 110 to 170 gigahertz, and it does have an overrange option to 175 gigahertz. And that's because you do have this wide IF, and sometimes you want to go a little bit above 170 and de-embed that. That seems to be supported, and these are the bandpass filters that come with it. If you look, we do have quite a wide range of attenuation, and as you adjust the attenuation, you can change the input compression. So with the maximum attenuation of 30 dB, plus 5 dBm is the measured input compression of the device, which is good. If you need more than that, you can have external attenuations, of course, added. And these are in 1 dB steps, so you can have really fine control of the dynamic range, which is also quite nice. This must be all in solid state. And then the displayed average noise level here, take a look, for example, at 148 to 166 gigahertz, we're looking at minus 152 dBm. So if you didn't know this was operating up to 170, these numbers are common like regular spectrum analyzers, so it's quite impressive. And we do have a measurement uncertainty of about 2.5 to 3.5 dB. At these frequencies, this is quite good. And if you look at regular spectrum analyzers at lower frequencies, having an uncertainty about 1 to 2 dB is also not uncommon. And these are pretty important specifications when you want to measure certain device that you want to have certain confidence in. Now let's look at this. Now the EVM is pretty important because a lot of people are trying to measure these broadband modulated signals at these frequencies. Now this EVM is the toughest situation because this is a cascade of the 170ST and 170SR in series. So basically their output of one is going into the input of the other. So all the imperfections, that includes phase noise, nonlinearity, just regular noise, everything is on top of each other, and these are the EVMs you get. And if you look, we do have a pretty nice flat region between about minus 32 dBm or minus 30 dBm to about minus 15 dBm, where the EVM is fairly constant. And at frequencies between 130 to 165 or so, we were looking at EVMs in the minus 36 dB, which is really, really good. And this is testament to the good PLL design, the low noise and high linearity, and allows you to basically measure in a wide dynamic range. Now, it'd be nice if this was a little bit further out because modern D-band devices do produce more power than this. And here you're linearity limited, and of course here you are SNR limited. But it's nice to see these kind of plots provided. Similarly, they also provide a phase noise plot, and this too is a combination of the 170 SE into the 170 SR, and this is the combined PLL noise that can add up if they're not correlated. So all this information is in the datasheet, but I did want to just point to it so you know that they are there so you can take a look. Now let's do the fun part and do some D-band measurements. Now what we need is a D-band source, preferably a source that can perform complex modulation that we can connect directly to the FE170SR and perform some analysis. And that's exactly what I have here on the right side. Underneath this block is an IQ direct conversion up converter that works between 110 GHz and 170 GHz. Don't worry about what's underneath the block. I cannot show the details of it, but it suffices to say that it has a very simple interface. It takes differential IQ inputs and an LO input, and it's going to perform all the necessary up conversions to provide us with a single transmitter output. Now, of course, it needs its LO and IQ source, and that's coming from two instruments up here. On the left side, the Rohde Schwarz SMP04 is going to provide the LO source directly to our up converter. And on the right side, the Keysight M8190A is going to be our IQ source that's going to get up converted. Now, the Rohde Schwarz SMP04 is not a modern instrument. They provide much better transmitters and synthesizers with a much better phase noise. So we should be able to see the phase noise impact on this directly on our measurement too, which is interesting. And back down here, we have the waveguide output of the transmitter going into a manual adjustable attenuator, and that goes into the input of the FE170SR. On the other side, the IF output comes out of this. And now you can connect this to anything you want, the FSW or the RTP, and in this case, I have it connected to the Rohde Schwarz RTP. And this is going to analyze everything for us because the firmware is designed to automatically communicate with the FE170. And take a look over here. The only thing coming back from the RTP is an Ethernet and a 10 megahertz reference. That's it. This is by far the simplest D-band setup I have ever put together. This level of abstraction is exactly what these frequency range measurements actually need. And there's also a bonus device over here, which I will show you later. This also operates between 110 to 170 gigahertz, part of the same family of products that Rohde Schwarz has announced. So let's go ahead and take a look over here and see what we can find. So let's see how easy it is to configure the Rohde Schwarz RTP to accept the FE170 as an external down converter and basically allow us to analyze the signal at D-band directly on the oscilloscope. And for that, we go under the menu, we click on the apps, and on the RF section, we can see that there is an external front-end option now. And if I click on that, you can configure how you want that external front-end to be connected. It's telling you to connect the reference output, which is 10 megahertz, into it, and take the IF output and bring it back into the RTP, which is exactly what we've done in our setup. And if I click on configure and go under the network section, all I did to accomplish this was to enter the IP address that shows up on the e-paper on the FE170. And then the RTP takes care of the rest with the firmware, downloads the appropriate parameters and sets everything up. And if I go under setting, I can enter what RF frequency I'm interested in looking at. And what the FE170 would do is it would take my desired RF frequency I want to look at, go and set the appropriate PLL frequencies internally, such that the IF frequency that comes out represents exactly this frequency at this IF frequency. So everything else is done in the background. I don't have to worry about this. So you can see 145 gigahertz maps into minus 9.9375, and here is a minus, most likely because it's on the upper or lower sideband. But no matter what RF frequency I set here, I will always get the same frequency, so it will map to the same frequency. So if I go over here, for example, and enter 120 gigahertz, nothing changes. It just changes the center frequency for me. The PLL does everything automatically. It will always remain at this IF. Now, I think it would be nice for them to change these parameters so that if the instrument knows FE170 is connected, like it displays down here on the channel, that it would map these so I don't have to worry about that frequency. But that's a minor complaint that they can definitely adjust with the firmware. Let's go back to 145 gigahertz. So a few other things you can set up. You can also apply your own LO externally if you want to manage the phase noise or the coherence however you want, and that's what this frequency would be. And you can also enable the LO output. You can see that here I have the RF attenuation automatically selected. If you set it manually, you can actually set it yourself, and that is pretty important to adjust and see where the nonlinearity terms come and go so that you can figure out if the nonlinearity is from your circuit or from the FE170, and these are pretty important things to play around with. You can adjust whether you're interested in EVM optimized and so on, some of the internal optimization parameters. But the beauty of applying an RF input and letting the instrument do everything is that because it makes sure that it places the IF and the RF and the internal PLL at the most optimum point because they already know the calibration coefficients of the FE170. So it's a nice setup. So let's go ahead and turn on our transmitter. Here we go. And check it out. Look how much information we're getting at once. And let's take a look at this and think about it. So what I'm doing is I'm injecting 100 tones into our IQ up converter. And those tones span 50 megahertz all the way to 1 gigahertz. And all of these tones are applied at the same time. So what we're seeing is the broadband image rejection of the D-band up converter. So what on this right side is the image of our up converter. That's pretty good. If you look at this, we're looking at over 30 dB of image rejection at 145 gigahertz. We do have a pretty strong LO here, which we need to address. And all of these at the same time allows us to analyze them in the same screen. Now remember that this flatness that you see and the absolute values of these tones coming out, those are calibrated to the front-end waveguide input of the FE170. These are absolute numbers, not relative numbers, which is very, very helpful if you want to understand. So here it basically tells us exactly how much LO we have coming out of the circuit. I have applied some external attenuation so we can play around with. We can also see some nonlinearities, which are the intermodulation of all of these showing up here on the left side. Let's see if we can address that LO leakage by adjusting some of the software parameters of our up converter. Okay, trying to apply some correction here. And take a look. We've addressed a whole bunch of the LO feed-through, and this is normal for an IQ up converter. You can actually adjust that by applying DC offsets to the IF inputs. And we're looking at this all at the same time, all over a broadband. This kind of broadband measurements, particularly broadband image rejection, is not something that's typically shown. And it shows you how good this IQ up converter actually is and how good FE170 is in analyzing it. And here now I've moved things around a little bit, and we're looking at 2 tones only. The span of the FFT is reduced to 250 megahertz, so we can see these 2 tones very clearly. They're only 5 megahertz apart, sitting at 50 and 55 megahertz. And the purpose here is to measure the IM3 and see if the front-end attenuation of the FE170 can be adjusted so that we're not making erroneous measurement. This is a pretty important feature of the instrument. So we're looking at 2 tones here, 50 and 55 megahertz, and I have placed cursors on the FFT so we can measure the output power and the IM3. If you look, these tones are around -5, -6 dBm each, and the delta Y here represents the third order intermodulation, the difference between one of these peaks to the third order modulation term, and it's about 30 dB. Now remember that both this delta, which is a relative value, and the absolute values here are all calibrated, of course, with respect to the front of the waveguide port. And we see the LO feed through here, we see IM2 terms, we see the image and the harmonics of the IF all in the same view here. Let's go ahead and adjust this, see if we can make this delta Y better, which is going to be quite nice. So we can go ahead over here again and go under our apps, under our RF front end, and start playing with some of the parameters. So we are telling the instrument that the RF level is a -10 dBm. Well, if the RF level is too strong, the IM3 terms are going to be dominated by the FE170 and not by our own IQ up converter, and that's what I want to make sure. So let's go ahead and change that and set it to 0. And what's going to do is going to change the front-end gain. You can see it reduce it by about 15 dB. Now if I go back over here, we can get rid of this. Look at that. The delta Y became 33 dB. So it actually became about 3 or 4 dB better because of the fact that we changed the front-end attenuation. And that means that it was not dominated by the IQ up converter, but rather by the front-end attenuation limits of the FE170. So being able to play with this, and remember, this is all electronic, built inside, it's pre-calibrated. And that means that you can make your measurement with much more confidence when you have this ability. Now there is another quick thing I want to try, and that is to see if the FE170 generates any spurious tones across a really wide IF bandwidth. Now you have to do this test across all RF inputs and all IF outputs, so of course it's a much more extensive test that I'm going to do right here. But I'm connecting the IF output into a spectrum analyzer rather than trying to do this test with a 10 gigahertz span on the RTP. And the reason is because the RTP itself has time interleaved data converters, and those can generate spurious tones, and we want to eliminate that. And by using a spectrum analyzer that has a pre-selector, you don't have to worry about this. So we're using the FSW here, which is a 26.5 gigahertz spectrum analyzer, and I have turned off all the modulations on our up converter, and I'm just simply putting out a single tone. So right now we're set to 145 gigahertz, where the center frequency would be here in the middle. And you can see there are no tones across an entire 10 gigahertz span, which is nice. And part of this reason is because of the frequency planning, the way they've done the PLL, as well as where they choose to do the IF to make sure there is no image from the FE170. Let's move this around the entire span and see what happens. So we can go up or down. You can see if I go all the way down over here, at some point we might see something, and we can study the effect of that. There you go. We can see a tone entering, and they're moving together. And we can stop over here and see where that is coming from. Now, you may be tempted to say that that's coming from our up converter. How can we find out? Well, I have placed a delta marker here. You can see the delta is about minus 48 dB. Now I can adjust the front attenuation, the external mechanical one that I have introduced. And that should have nothing to do with the relative difference of these two. That attenuation should move both of these up and down if that is coming from outside of the FE170. Let's try that. I'm going to introduce some attenuation. And we can see bring it all the way down to around here. And look at that. The difference actually grew. It became minus 56, minus 57, whereas it used to be minus 48. So that tells us that that is indeed coming from inside of the FE170. But you can adjust the front-end attenuation, and that actually gets better. So it's some tones generated inside. It's impossible to make everything perfect. This needs to be more extensively tested, but because you do have the external attenuation to play around with, it's very helpful to eliminate these kind of things during testing. And for completeness, let me make sure that I go over the entire range. So here is all the way at the edge. There you go. The power is going down. That's because our up converter also has a frequency band limitation. And then we can go all the way to the other side. So you can see that tone will go to the edge and it will leave the screen. We can keep going. It's very, very clean. And we go all the way up here, all the way to the other end. And there's a little tiny tone down there. Again, remember, we're talking about 60, 70 dB spurious free, so it's really not that big of a deal. Yeah, very nice. And this is a huge, huge improvement over traditional ways of doing this. If you've ever used some of the classic down converters that don't have image planning and so on, you'll see how advantageous this actually is. And similar to the RTP's internal firmware, the Rohde Schwarz VSE can also detect the FE170 and correct for it, and essentially treat it like an external down converter with all the benefits that it has being connected to the RTP. So here's a flow of some signal that I'm trying to analyze using the VSE. The signal coming in is a 2 gigabaud or 2 giga symbols per second, 32 QAM modulation. So there's a lot of data coming through, and the carrier is 145 gigahertz. We're going to capture 4096 symbols. We're going to process that and apply equalization and correction so we can see the EVM of the signal and analyze it. And in the back, you can see the EVM of the 32 QAM signal. Now, I have added a very particular and difficult to catch impairment to this 32 QAM signal. And every once in a while, you might be able to see it. Every 10,000 symbols or so, there's a shift and an added phase noise to the signal. And you can see that by the blurring of the dots on the constellation every once in a while. And we can catch that. And if you look at the EVM in percentage or the EVM in dB, you can see every once in a while it jumps up and jumps back down. And that's because we just happened to capture during the time where it was having that impairment. Now, this is a very tough measurement to do, even at lower frequencies. So the fact that you're doing a fully calibrated measurement at D-band, all built in without having to worry about it directly on the instrument, is really quite impressive. Testament to how easy they've made using this instrument and how seamlessly it's built into the software. Now, there are bugs and things here and there. This is an early firmware revision. Sometimes the software crashes and so on, but I think those things are going to be fixed over time. Just the ability to be able to make these measurements like you're doing it at lower frequencies is quite nice. If I hadn't told you this was a carrier of 145 gigahertz, it'd be hard to know that otherwise. And VSE has a lot of different applications built in. You could do hours of video of just what the VSE can do, and it competes with other types of vector signal modulators from other competitors as well. And you can see all the information coming in and out of it. We can perhaps revisit this and do more experiments, but I wanted to capture something and show you that you can just treat the VSE like any other software, any other carrier, now extended from 110 to 170 gigahertz. And I promised to show you this bonus device. This is the brand new Rohde Schwarz NRP sensor that works from 110 to 170 gigahertz. It's just been released and it is ridiculously fast. If you've ever used any other power sensors that operate roughly in this frequency range, you know what I mean, especially at low input powers. As far as I know, there's nothing else like this in the industry that is banded for 110 to 170. This is a thermal detector, of course, and it works from minus 35 dBm to plus 20 dBm, and it connects to the existing NRX, for example, and I'll show you that in a second. So I basically removed the FE170 and I put this exactly at the same port FE170 used to be. So we can measure the output power coming from the transmitter and adjust it with this mechanical attenuator so we can see the NRP in action. Now the NRP sensor is rated down to minus 35 dBm, and that's essentially supposed to be its floor, but it does measure quite a bit below that, which is nice. You do want to have that margin so that minus 35 you're measuring with confidence. Now everything is turned off, there's no power going into it, so I'm going to go ahead and enable the LO of the transmitter, and right now I have the attenuation at its maximum, and you can see even that you can actually detect that there's a little bit of power, which is quite impressive. Let's go and turn this and see what happens. Look at that. Look how fast the update rate is at these input powers. That's pretty impressive. So here's minus 30, for example. You can continue. And there you go. We can see the maximum power coming from the transmitter about minus 1 dBm. This is a fully modulated signal, and the thermal detector detects everything at the same time, of course, and we have no problem detecting that. Now, if I change the attenuation very, very quickly, is the thermal detector, so you're going to have to wait a little bit until it settles down, but it will settle down. It'd be nice if the NRX has some firmware in there that tells you something about the confidence of the measurement. That's a little bit difficult to do because you don't know, but perhaps based on the trend, they could tell us. But look at that, it goes back to where it was. We can go back all the way again, back to where we were. Perfect. I mean, this is such a useful thing in the lab, and there has been nothing like this, so we're quite happy to be able to use this too. Now, having said all that, it doesn't mean that the FE170SR cannot be improved. There's definitely things they can do with the firmware to make it a little bit more stable and easier to use, abstract things even further away, and make sure that the swap mode is fully supported in the spectrum analyzer. As of recording of this video, is still not fully supported. At the same time, you can add things like electronic pre-selector to this, which it doesn't currently have. You can improve the linearity, and the list goes on. But this is a fantastic platform to start with. I'm sure that they're thinking about these improvements with future revisions of this. And there you go. I hope you enjoyed the overview and experiments with the Rohde Schwarz FE170. It's a fantastic instrument and a great addition to the already nice lineup of RF equipment that Rohde Schwarz offers. There's a lot of activity happening in the Rohde Schwarz in the past couple of years, and it's been nice to see them innovate and refresh and really push the boundaries on what they can produce. And I'm looking forward to all the great things they're going to do in the future. As always, let me know what you think in the comment section, or if you have any questions, I'm happy to answer that. This is going to go back, so I can't do any more experiments with it here in my lab, but I'm glad to see that it's been released finally in the industry. See you next time.